Fix two real numbers, a and b. The random variable indicator that x is greater than a multiplied by a is integrable, since it is almost surely less than or equal a. Linearity of expectation gives the expectation of x minus a plus that the positive part is equal the expectation of x multiplied by the indicator that x is greater than a minus a times the expectation of the indicator that x is greater than a. We're allowed to take a out of the expectation, of course, because it's just a constant. This, since x has a density function little f, can be written on the left hand side by the integral from a to infinity of x against the density, and on the right hand side a multiplied by simply 1 minus capital F of a, the cumulative distribution function. So the CDF always exists, density doesn't always exist, but in this situation we've been given that it does. And then that's just by definition, and since the expectation of an indicator is a probability. Therefore, if we take now the difference of the expectation of x minus a plus and x minus b plus, we get the difference of the two integrals minus the difference of a and b both multiplied by 1 minus the CDF at those points. Now we can integrate the left-hand side by parts, or rather do the no, that's right. Since capital F is the antiderivative of little f, integration by parts allows us to get b fb minus a fa, which will of course cancel with this part, and an integral from a to b, differentiating x, take the antiderivative of little f. So here, then writing what we already had. Cancellation of the terms on the left and the right. Leaves us with the solution that we wanted. Now for the second part of this question, we want to show that capital F and little f are fully determined by the values of these expectations of x minus some constant, the positive part of that. The mean value theorem gives that there exists a constant c in between our fixed values of a and b, such that f at c multiplied by the difference b minus a is equal to the value of the integral of f on the interval a and b from a to b. This we should take here without loss of generality. We can take b larger or equal a. although it should also would be true for less than or equal, but just for ease of notation. So this implies that if we took a limit of the interval a to b, getting smaller and smaller and smaller, the mean value theorem still holds for every interval. We should be able to pin the value of c basically to a point exactly where we want it by taking the limit of the interval to that point. Since we can choose a and b freely, we can just take a to be that somehow target point and take the limit as b goes towards a, and we should pin the value of c at the point a. So what it implies is that the limit as b goes to a of 1 over b minus a, the integral from a to b, fx dx, since this is equal to f at c for some c in between a and b, for any choice of a and b, this limit then is equal to fa plus, it's not necessarily equal to fa, but it's equal to the limit of capital F as it goes towards a from the right hand side. The problem is that capital F need not a priori be right continuous. But since f is a cumulative distribution function, we know that in this case it is right continuous. But for a general function, of course, this strategy doesn't give you the value at the point, it gives you the limiting value from the right hand side. Now we can just use part A to show that this limit can be expressed in terms of these functions, these expectations of differences between x and a constant plus that we want to show that the function is determined by. So thus fa is equal to the limit as b tends to a of 1 over b minus a multiplied, now substituting in the value that we have from part A, of b minus a minus expectation x minus a plus expectation x minus b plus. Let's make that clear. This is the square bracket. We can cancel out one of the b minus a's and take that out of the limit. But this is just like notation now. Essentially, we're moving things around. Over. I'm thinking b minus. No, they got minus outside, so b minus a on the bottom. So that gives it capital F can be expressed now. If we know all of the expectation of x minus k plus for the constant values of k, then we can fully determine f at any real value, because we can describe it in terms of this limit of these functions that we already know, divided by some constants, but that's not an unknown quantity. Now I want to show the same for little f. So another application of the mean value theorem gives that for all real numbers, f of a sorry, not f of a plus is equal to the limit as b goes to a of the integral between a and b, just using exactly the same logic as we had before, which that should be, of course, 1 minus b over a in there. So that's can equally be written with the antiderivative of little f, that's capital F, so f of b minus f of a over b minus a. So just doing exactly the same as we did before. I've skipped the step of writing out the mean value theorem, but no different logic there. The problem is little f, the density, is not necessarily right continuous. So capital F is by definition, little f need not be. But since capital F is absolutely continuous with respect to the Lebesgue measure, which is exactly the condition that it has a density at all. So that is the condition that f exists. F exists if and only if capital F is absolutely continuous with respect to the Lebesgue measure. It must be everywhere differentiable. And therefore, f at a point is equal to the derivative of capital F at a point which is by definition also equal to fa plus. That's just the definition of the derivative of f of capital F at a point is given by this limit here, what we just described as being equal to little f at a plus, right, from the mean value theorem. But that's just a definition of the derivative of capital F at that point. So little f is equal to this derivative at almost every a. And that is almost every with respect to Lebesgue measure. That is, there exists a set B, subset of the real line, such that f of a is equal to f dash a equals f a plus for all elements in the reals take B, and the Lebesgue measure, sometimes written with lambda, sometimes written with the words Lebesgue, like that, oops, of B, is equal to 0. And therefore, since capital F is determined, uniquely determined, by these expectation x minus k plus, which was what we just showed above, so is f on R minus B. So little f is uniquely determined by these expectations on the reals minus some Lebesgue null set. What it remains to note that f is only defined up to Lebesgue null sets. What that means is that f as a density is only defined on the real line minus some set of Lebesgue measure 0. The reason for that is that it's defined by a Lebesgue integral, and sets of Lebesgue measure 0 don't change the value of the Lebesgue integral. So you could change the value of f on a Lebesgue null set and it'd still be the density of capital F, because the Lebesgue measure over that function won't change. So therefore this fully defines f, right, as far as it's possible to define little f. That then finishes the question.